Sweet. I think, yeah, as folks continue to come in, we could just get started. But yeah, thank you all for joining today. Super excited to have Valentin here with us. So for context, I'm Raj from alphaXiv, and we help you keep up with and apply the latest AI research. And one of the things we are also very passionate about is community events, and we work very closely with Vals on doing events in AI Evals. So yeah, with that, I'll let Nikhil take it from here.
Cool, fantastic. We're super excited to host Valentin. Been a big fan of his work. He's a postdoc at AI2 and University of Washington, and he works with Noah Smith and Hannaneh Hajishirzi. And today, he'll be talking mainly about his work on fluid language model benchmarking, which is a new evaluation approach that helps you dynamically select items based on the ability level of a model. And more broadly, he'll be also sharing some of his thoughts on the eval landscape. So the talk is recorded. We'll have a Q&A session at the end. But also, if you have questions during the talk, please post them in the chat and we can ask them. But yeah, otherwise, take it away.
Thank you. Yeah. Hello again. I'm Valentin. I'm very excited to be here. And I'm going to talk about fluid language model benchmarking, which is a paper that we recently presented at Column, and also a method that we've been working on for quite a while now. And so, as Nikhil said, if there are any questions on the way, please feel free to just ask them. I think we have a lot of time, and I'm happy to answer any questions as we go. I want to start by taking a quick look at the benchmarking landscape at the moment. Here we are. So yeah, I think we are all aware that there has been this massive proliferation of benchmarks over the last few years. There's now a broad variety of different benchmarks that people are using to evaluate all different capabilities and different types of properties of LLMs and AI models more generally. And even though benchmarks are very useful, there are also quite a few challenges that we face. And I think, we are probably aware of many of those challenges. And it's actually also, it has become much more visible in general. So there is an upcoming NeurIPS paper that reviewed, I think, more than 400 AI benchmarks. And this was actually even reported on in the news. So like LLM benchmarking is now very popular. And before I talk in more detail about fluid benchmarking and how we try to address some of those challenges, I want to quickly give you a background on what are some of the use cases that we think about and what are some of the challenges of LLM benchmarking. So let's start with the use cases. I think the most popular use case that we are all familiar with is leaderboarding. So let's say we have one benchmark like MMLU or a set of benchmarks that we collate into a bigger benchmark, and then we can evaluate a set of models on those benchmarks and rank them. And so this is what we very commonly do, and many people are interested in those leaderboards, like for example here, the OpenLLM leaderboard, but there's a broad variety of different leaderboards. I mean, there are various issues with those, with the benchmarks, with this kind of leaderboarding, but I think it's a very, very popular use case. A second use case is based on those leaderboards to then advertise models. So whenever you have a big model release like we have today with Olmo 3, or like the example here of GPT-5, you report scores on those benchmarks to then advertise the quality or like the range of capabilities that your model has. And then finally, one other use case I want to quickly mention is during model development, right? So throughout the model development pipeline, starting with coming up with the training data, deciding on data mixes, to different training hyperparameters, benchmarks in a way provide us with some sort of guiding compass, which we use to make our decisions. So here, for example, this is from the AMBER technical report, where they show how the performance on different benchmarks changed as they trained the model. Now, in all of those areas, there's quite a few problems, and I want to quickly highlight 3 problems that I think are particularly relevant. So one is the problem of label noise. There has been quite a bit of work now showing that even in the most popular benchmarks, like MMLU, here, for example, many of the questions have the wrong ground truth label. So if you look at the bottom right here, the wrong ground truth, like this is one class that was identified in a recent NACL paper. And so this would be a case where in a multiple choice question, the ground truth gold label is actually incorrect, but one of the other answer options is actually the correct answer, which means that if you have a model that knows the answer to the question, it's going to be counted as incorrect. And if you have a model that does not know the answer, in 1 out of 3 cases, it's actually going to be counted as correct. So this is a huge problem because it really makes evaluation on such benchmarks quite noisy. And I should say that in the case of MMLU, in some of the subsets, it's more than 50% of the questions that have a wrong ground truth, which they show in this paper, which is really very concerning. A second problem that I want to quickly highlight is evaluation costs. So it can be incredibly expensive to evaluate a model on a single benchmark. This here is from the Helm technical report, and they actually show how much they cost for how much they paid for evaluating some of the models. And for example, in the case of J1, it cost them more than $10,000 to just run one single evaluation run of Helm on this model. And now assume you want to run this repeatedly during pre-training, this can quickly become a bottleneck. So making evaluation more efficient, I think, is a huge challenge that we need to think about. And then finally, there's the very well-known problem of saturation. So this here is a plot that Dow creates and I think updates regularly, which shows how performance of models changes over time on some of the most popular benchmarks. And you can see that over time, for most of those benchmarks, we have reached or already surpassed what is the alleged human performance on those benchmarks. And so in that way, they lose value for evaluating the models. I mean, one problem also is, of course, that people start to use those benchmarks and train their models on them. But there's one other perspective on saturation that I want to quickly mention here, and this is saturation during pre-training. So when we are in this model development setting and we want to use benchmarks to see how we are doing during training, there's also this issue. If you look at those benchmarks here, this is, I think, from the K2 technical report. The GSM-8K example here on the right is what we want to see, right? We see continued improvement to the end of training. So we know even at the end of training that we are still making progress. But then if you look at ArcEasy or RACE, we don't really see that, right? In the second half, it's unclear. Are we still really making progress? Like, is there something wrong with model training? So in the context of pre-training or model training more generally, there's also a notion of saturation, which is connected to but slightly different from this notion of saturation over years, for example. Now, it's very interesting to think about that in the context of human testing. So in education, some of those problems exist as well. For example, the problem of costs, right? Ideally, you would want to have a very, very large collection of questions that you would want to give to a student, but you can't because you are limited in time. And in education, there is a subfield of education at the intersection between education, statistics and psychology, which is psychometrics, where people have thought very carefully about how to mitigate those issues. And psychometrics has developed a certain number of technical and statistical approaches, for example, item response theory, that have been shown to really substantially mitigate those challenges. And as a result of that, psychometric methods and, for example, item response theory are now the common form of doing evaluation in the context of educational testing, like GRE, SAT, they are all based on IRT and different methods from IRT. So what we were wondering in this paper was, can we leverage some of the methods developed by psychometrics and in the context of education to mitigate some of the issues that we are facing in LLM benchmarking today? And we make 3 more specific contributions here. So the first contribution is that we adopt IRT, so item response theory, to measure characteristics of benchmark items, for example, the difficulty of individual items in a benchmark. Then, based on that, we introduce a method that we call fluid benchmarking that uses IRT to dynamically adapt benchmark items to a language model capability level. And then in the third part, we conduct a series of experiments that show that fluid benchmarking indeed improves evaluation quality along several dimensions. And here I'm going to specifically talk about the validity of evaluation, the variance, and the efficiency. All right, okay, so let's start by talking a little bit about IRT. So what is IRT? The basic idea of IRT is that you have a benchmark, and so here like we refer to each question as an item, right? So each question would be like a multiple choice question, and MMLU is one item. And the basic idea is that we take a population of LLMs that we evaluate on all of the items in our benchmark. And then we can analyze the response patterns of all the LLMs on each item to learn useful characteristics of those items. For example, if you look at item 1 here, you will notice that all the LLMs got item 1 correct. If you look at, for example, item 6, you will see that none of the LLMs got this item correct. And so this indicates that maybe item 1 is easier than item 6, right? So you can use those response patterns to learn something about the difficulty of those items, which is like one useful property, right? So if you know the difficulty, you could, for example, say, oh, I want to create a more difficult version of this benchmark. Or I know I have a very weak model. I only want to evaluate on the very easy instances from my benchmark. So this is already can be a useful property that we can learn by analyzing a population of LLMs. Like the actual IRT models that we use are more complicated than that. The specific model that we use here is what is called a 2-parameter logistic model. So each item is represented by 2 parameters. But let's first start by looking at what do we actually try to estimate here. So the probability here that we try to estimate using this model is the probability that a certain LLM answers a certain item correctly, right? So we haven't evaluated the LLM yet, but we try to estimate what is the probability that this LLM is going to answer a certain item from our benchmark correctly. And you can see that the mathematical form that we use here is a simple logistic. And so let's take a look at the specific parameters that we have here. So A is one of the 2 parameters for the items. And this is the discrimination of an item. It tells us how sharply a specific item distinguishes between better and worse LLMs in general. So that's an item parameter. I think it will become more clear when we actually look at representations of those items in a second. B is the second item parameter. And this is the difficulty. It basically tells us the ability that a certain LLM needs to get a 50% chance of getting a correct answer on this item. And in general, like the higher the difficulty of an item, the higher the ability of an LLM needs to be in order to get a high probability of getting this item correct. And then finally, we have one parameter representing the LLMs, which is theta, which is the ability. And so this, like the idea is that we use an IRT model to estimate the ability of an LLM, and then we can use the ability of the LLM as some sort of performance measure instead of accuracy or more standard evaluation measures that we might want to use. Now, how does this actually look like? So here's a couple of like one way of thinking about this is that you can represent each item as a curve. These are called item characteristic curves, and these are like simple logistic curves like here. If you compare item 1 and item 2 here, they have the same difficulty. So the difficulty is essentially the location of these curves. And the discrimination, A, is essentially the slope. So if you compare item 1 and item 2, item 1 has a very high discrimination. So if your ability is only slightly higher than 0, it's already very, very likely that you're going to answer this item correctly. And by contrast, if your ability is slightly lower than 0, it's very unlikely that you're going to answer this item correct. Now, if you take a look at item 2, even if you have a very, very high ability, it's not necessary, it's not clear whether you're going to answer this item correct or incorrect. So item 2 could, for example, be a mislabeled item, right? If you think about a mislabeled item, for a mislabeled item, very good models are going to get this item correct, and very bad models are going to get this item incorrect. So ability is a very, very bad predictor of whether you are likely to get this item correct or incorrect. So mislabeled items, and we actually also show this empirically, for example, could be items with a very low discrimination. Now, if you compare item 1 and item 3 has the same discrimination. It's a high discriminative item, but it has a higher difficulty. So in order to get a high probability of getting this item correct, you need to have a better or a higher underlying ability. So this is like in the 2PL model with 2 item parameters, this is how you can think about items. I think we already might have a couple of questions on the chat. Let me
Yeah, there's a couple of questions from Daryl and Jacob.
yeah. So maybe I might take the Daryl's question later. Let's maybe because I think Jacob's question seems to be directly related to what I'm talking about. So the question is, can I think of the discriminatory power as a measure of its quality? Yes, I think it's one way of thinking about this. Like in general, if you look into the psychometric literature, high discrimination items are generally preferred, right? Because they just give you a better signal about the underlying model capability. And I mean, we did some analyses, and in fact, if you take, for example, something like MMLU Redux, where people actually went through the MMLU items, and so they annotated mislabeled items, and we measure their discrimination based on an IRT model, they tend to have a very low discrimination. So in a way, for example, by filtering out low discrimination items, you might already remove most of the mislabeled items from your benchmark without having to hire annotators like human experts that actually understand virology or anything like that. And I'll talk about this later. So yeah, we will come back to that. All right, okay, so let's quickly take a look at how we actually fit those IRT models. So I think I gave you a general idea, but how do we actually do it in practice? So what we need is we need a population of LLMs that have already been evaluated on the items for which we want to get an IRT model, or that we, as people who want to train IRT models, then evaluate on all the items of our benchmark. And so, I mean, ideally, you would want to have a couple of dozen, maybe a couple of hundred LLMs. So of course, the more the better. What we did in this study is we just downloaded existing evaluation results from the OpenLLM leaderboard, which comprises 6 benchmarks: Arc Challenge, GSM8K, HellerSwag, MMLU, Truthful QA, and We Know Grande. I think the OpenLLM leaderboard has thousands of models. We did some sort of filtering and boiled it down to 100 models. And then you use Bayesian techniques to actually fit the IRT model. So here we used MCMC and hierarchical priors. So we had normal priors on the ability and the difficulty parameters, and a log normal prior on the discrimination parameter, and then hierarchical priors on top of that. Now, you can then visualize the item parameters for all the items in your benchmark. So for example, here, this shows you the discrimination parameters of all the items in each of those 6 benchmarks. And you can see that, for example, HellerSwag has many very discriminative items. So like this doesn't tell you anything about the difficulty. These might still be relatively easy items, but these items are very good at distinguishing models that are around this difficulty level. And we also see, like in practice, that HellerSwag is a very smooth benchmark. So it's very useful for model development, for example. Now here you can see the distribution of difficulty values. And for example, HellerSwag, as you can see here, is a relatively simple benchmark. So it might not be as useful to compare very strong models. By contrast, like MMLU has more difficult items compared to HellerSwag. So you can do these kinds of discriminative or descriptive analyses of model benchmarks and use this, for example, to do item filtering or something like that. Now, what you eventually might want to do is you want to use, as I already mentioned, you want to use these item parameters to then estimate the ability of an LLM, right? In the end, we are interested to compare different LLMs to see how good are those LLMs. And so what we need to do in IRT world is we need to estimate their ability. And I have an example here that shows why this might be beneficial compared to just computing accuracy. So let's say we have this toy benchmark consisting of 2 items. Item 1 has a very high discrimination. Item 2 has a very low discrimination. So as we said, item 2 might have certain problems. It might be mislabeled or something like that. And so here we evaluate one LLM on this benchmark, and this LLM gets item 1 correct and item 2 incorrect. So in terms of accuracy, it would be 50%. If we take the IRT approach, we would say we try to find the ability that maximizes the likelihood of this response pattern under the IRT model. And if we do this for this IRT model here, then we find that the ability with the maximum likelihood would be 0.5, right? Now, let's take a look at a second LLM. The second LLM gets item 1 incorrect, item 2 correct. So in terms of accuracy, it would be the same, 50%. But if we take the IRT approach, we would try to find the ability that maximizes the likelihood of this response pattern. And this is actually minus 0.5. So what you can see here is that, in a way, the IRT model puts more weight on getting the high discrimination item correct than getting the low discrimination item correct. And so given that the first model got the high discrimination item correct, this is counted as more important. And so this is why this model gets a higher ability than the second model. Oh, there's the question, do we need a prior? Yes, this is a little bit simplified here. Typically, we would not do an MLE, we would do a map estimate. So you can use different priors, and that's a great question, yeah. I'm just looking at the other questions. There's one question whether the ability broadly correlates with accuracy. Yes, that is the case. If you compute the correlation, it also depends a little bit on the specific IRT model that you use, but it's generally very high. But if you look at specific model comparisons, there can be differences. And there is, maybe if we have time in the end, I can talk about one example where there's really a huge difference between doing the ability estimate and actually computing accuracy. All right, okay, let's move on. So you might already see that this kind of taking item properties into account can be useful in practice, because you would hope, for example, that it increases the validity of your evaluation. And in fact, we are not the first to observe this. There has been quite a bit of work in NLP and AI more generally using IRT to improve evaluation. But all of those studies that have come out over the last few years, they used IRT to then, in the end, create some sort of static set of items that you evaluate on, right? So for example, you do this discrimination analysis and you throw out all the low discrimination items, and then you just use this higher quality item subset for evaluation, but it's still static. And there are certain contexts, like, for example, evaluation during pre-training, where this might not be ideal, right? Because you would expect that the performance really shifts quite a bit during over the course of training from a random model to a perfectly capable model. And so having these static item subsets might not be ideal. So let's think a little bit about how can we make evaluation more adaptive. And so this is what we're actually doing in fluid benchmarking. So let's take a look at our fluid benchmarking. So to give you an idea of what is the problem of these static subsets, we did this simulation study here, which I find quite interesting. So what we did here was we said, let's simulate a pre-training run, and we just assume that the performance improves linearly. And we start with an initial ability of -7, and we say that at the end of training, our ability is +7. And then we took an IRT model trained on HellerSwag, where we have item parameters for all the items, and then we computed how informative are the different items from HellerSwag relative to the different ability levels that we observed during pre-training. So here on the upper panel, we show the Fisher information. On the y-axis, you can think about all the items of HellerSwag stacked according to their difficulty. So the most difficult items are at the very top, the easiest items are at the very bottom. And so we compute the informativeness here using Fisher information. We will talk later a little bit more about Fisher information. So for now, just understand this as some sort of measures of informativeness. And so you can see that as we train our model, the areas of the benchmarks of the benchmark that are most informative for the current ability level really shift. So at the beginning of training, the most informative items are the easiest items. And then at the end of training, the most informative items are the most difficult items. So ideally, we would want to have some sort of evaluation protocol that would take this into account. And this is the underlying motivation of fluid benchmarking. And now, when we look into psychometrics and what people are doing in education, this is actually exactly what they are now doing for most of those tests. So in education, this is called like computerized adaptive testing. So where the idea is that you know the difficulty of all the questions. You also have like more item parameters, but like for the purpose of this example, let's just think about difficulty. And so if you have a very weak test taker, then the questions are getting easier and easier as you evaluate this test taker. And like for more capable test takers, the questions actually get more difficult over the course of training because the evaluation adapts to the underlying ability of the student. And so there's been a lot of research in statistics and in education showing that this makes evaluation more efficient, and it also has other nice benefits. So for example, it gives you better quality control. You avoid these like problematic instances because they, as you will see in a second, they don't really show up that much, which is one of the reasons why most of these standardized tests that you can take in the US today, like GMAT, GRE, SAT, they all do adaptive testing. So let's take a look at how we took this concept of adaptive testing and how we applied it to LLMs. So let's say we want to evaluate an LLM. What we do is we start with just one item from our benchmark, which is always the same. So the first item that we use is always the same. It's an item with an average difficulty. We then evaluate the LLM on this one item, and depending on whether the model got it correct or incorrect, we do an initial ability estimate. So we use the underlying IIT model to estimate the ability of the LLM. And then based on this estimated ability, we select the next item, we evaluate that item, and then we update our ability estimate. So we have this loop where we pick an item, we evaluate, we update the ability estimate. Of course, the key question here is, how do we actually select the item? And we again use Fisher information here. And I now want to explain this in a little bit more detail, like why is this useful? So you can see that the equation here is actually A, so the discrimination, B, the difficulty, and theta, which is like the current ability estimate. So you see that we have A square. So this means that items with a high discrimination are generally preferred. Or put differently, if you have a very low discrimination, it makes it very unlikely for an item to be picked, which is nice, right? Because as we have discussed, low discrimination items are generally of low quality, so they only show up at the very end of fluid benchmarking, or not at all if after k items we decide to stop the evaluation because we are already content with our result. And then notice that we have these theta minus b terms. Their effect is that we generally prefer items whose difficulty is close to the ability of our model. So this adaptability that we talked about comes in right here because we pick items whose difficulty matches the ability of our model. Now, one like more detail about like Fisher information. So here's how this actually looks like in practice. So we fix theta here at 0. So we say the ability of our model is 0. And then the dots here are all the items again of Heller swag. And so you can see that in a way, there is this interaction between discrimination on the one hand and difficulty. So if your difficulty, the difficulty is on the x-axis, if your difficulty is very far away from the ability, it's very unlikely for an item to be picked. And if you are very close in difficulty to the current theta estimate, you still need a high discrimination to get a high Fisher information and hence a high probability of being picked as the next item in our evaluation. Now, here's a toy example of how fluid benchmarking actually looks like. So let's say we evaluate this first LLM. This is a very good LLM. We start with an item of average difficulty. This LLM gets this correct. So the ability estimate is going up. So the next item that we are going to pick is going to be more difficult. This LLM gets even the next item correct. So so the ability estimate goes up. The next item is going to be even more difficult. So you can see that like the difficulty of the items that we pick goes up after each evaluation. And by contrast, here we would have a weaker LLM. And so here the difficulty goes down because the ability estimate goes down. And then the items with the highest Fisher information are going to be items whose difficulty is also lower. Now, one thing that might be confusing initially and that I want to highlight here is that these two LLMs are evaluated on different sets of items. So the only item that these two evaluations have in common is the first item, and this is always going to be the same. But apart from that, the three other items are different. If you were to compute accuracy, this wouldn't really work, right? Because I mean, yeah, in this particular example, it would work, but in general, it wouldn't work. You couldn't compare accuracy on different sets of items. But here, given that we, based on these model responses, we try to estimate the underlying ability, and the ability is estimated in a common space, we actually can compare evaluation results for LLM1 and LLM2. So that's the nice thing. We evaluate on completely different items, but in the end, we do this ability estimation, and then we can compare across LLMs. Okay, so let's take a look at our experiments. So as I already mentioned, we focus here on evaluation during pre-training, where capabilities are evolving quite rapidly. And so this might be a very good setting for testing this adaptability. We take 6 LLMs where checkpoints are publicly available. And so I think we sample between 60 and 80 checkpoints for each of those models. And we evaluate them on the 6 board. The IIT model that we use here is also based on the OpenLLM leaderboard. And in the paper, we look at various prior evaluation methods. Like here, I'm just going to talk about standard accuracy, which I think is the most relevant evaluation method in practice. And we always match the number of evaluation items between fluid benchmarking and standard accuracy. So for standard accuracy, we just randomly sample k items and compute accuracy on that. For fluid benchmarking, we do our fluid test, and then we stop after k items. As first, here's a sanity check. So does our evaluation indeed adapt to the capability level of an LLM? So here we look at the training run of Olmo 2. On the x-axis, you can see all the checkpoints. And on the y-axis, we again have the items of Hella swag stacked according to the difficulty. So the most difficult items are at the very top, and the easiest items are at the very bottom. Now let's take a look at the first checkpoint of Olmo, which is essentially still a random model. So here you can see the items that are being picked by fluid benchmarking for this first checkpoint. We start with this item close to 0. This is always going to be the same item with an average difficulty. Now, given that this is a random model, the model does not get this correct. So the next item that we pick is going to be easier. The next item that we pick is going to be even easier. And so we go down and down in difficulty until we reach the easiest items that we have in Hella swag. Now, as we train the model, you can see that the areas of the benchmark that we focus on become gradually more difficult. And at the end of training, when we have a strong model, we focus on the most difficult items in our benchmark. You can also see that there are these a little bit weird looking lines. So for example, there's this one line at 0. This is because we always start with the same item, right? So irrespective of the current ability, we don't know that we already have a very strong model at the end. We start with an item of the average difficulty. And then if you think about it, if you evaluate on this one item, there's only 2 options of how the ability estimate can look like after evaluating on this one item. And so in a way, the second item that you pick after the first item, there's only 2 options. And so given that you always have these binary choices on which item you pick, you get these lines. So for example, this line here is the item that you jump on if you've gotten the first item correct. And then this line here is the third item that you would pick if you got the second item correct, and so on. So you get these lines that show you these relatively structured paths that you take through the benchmark as you do fluid benchmarking. We then also try to measure the quality that fluid benchmarking gives us. And we looked at different dimensions of evaluation quality. We looked at validity, variance, efficiency, and saturation. So let's start with validity. So what we mean here is when we do evaluation on a benchmark, I mean, we are, on the one hand, we are interested to see what is the score on this one benchmark, but why we actually do evaluation is we want to know whether the model has a certain underlying capability. So we would hope that the evaluation on this one benchmark generalizes to other benchmarks that measure the same capability. So this is like this notion of external validity. And so what we did here was we created these pairs of benchmarks that measure the same underlying capability or roughly the same underlying capability, like for example, 2 common sense reasoning benchmarks. And then for each model, we computed the rank that we get on one benchmark and the rank that we get on the other benchmark. And then we computed the rank distance between these 2 ranks. And ideally, if we have an evaluation protocol with a high validity, evaluation on one benchmark would generalize nicely to the other benchmark. So we would hope to see low rank distances in general. And so we did this for accuracy and for the ability estimate that we get based on fluid benchmarking. So on the left-hand side, you can see for standard evaluation, this is one example, we look at different checkpoints of our model, and you can see that throughout model training, there's quite a bit of fluctuation, and sometimes we are pretty far off from the true rank of the model. By contrast, for fluid benchmarking, we are much closer to the true rank. So the external validity of evaluation that you get using fluid benchmarking in general is much higher than for standard accuracy. And so this is like the example of one model on one benchmark, but we found this really across the board. One reason for this, and I've already hinted at this a few times, is that if we do fluid benchmarking, we effectively avoid mislabeled items. So the analysis that we did here was we looked at tests of 100 items. So for standard evaluation, just randomly sampling 100 items. So we did this for MMLU, randomly sampling 100 items from MMLU. And for fluid benchmarking, doing like a fluid benchmarking test with 100 items. And then we counted on average how many mislabeled items would we expect for these 2 ways of evaluating a model. And so we found that we can reduce the probability of encountering a mislabeled items by 2 orders of magnitude, by more than 99%. So we, given all the properties of fluid benchmarking that I've talked about, these mislabeled items, they would be evaluated on only at the very, very end of fluid benchmarking, and typically we stop our test before then. Then let's take a look at variance. So one other concern is that we have certain benchmarks give us very, very high variance training curves, which then makes it very difficult to trust into any individual evaluation. So here's one example that shows you the training curve for standard accuracy on one model with a certain number of items. And this is the curve that we get using fluid benchmarking for the matched number of items, matched benchmark, and matched model. And in general, the training curves that we get using fluid benchmarking are much smoother and give us a much better signal about training progress than for standard evaluation. Now, these 2 benefits of increased validity and lower variance, they are particularly pronounced for small item sizes. So if we compare how the quality of evaluation changes as we look at smaller and smaller item subsets, you can see that for standard evaluation, the quality really goes down. So higher numbers here are generally lower performance. And for fluid benchmarking, we lose much less in evaluation quality. So for fluid benchmarking, if you compare the results for 50 items, they are already better than for standard evaluation with 500 items. So you get this combined benefits of better efficiency at the same time, increased validity and lower variance. And then finally, we also looked at saturation in the sense of this saturation during pre-training that I talked about in the beginning. And so here, the thing that we measured was essentially the correlation between the checkpoint IDs and the performance. So what we would hope to see is that performance is increasing throughout the training run so that we have a very high correlation. And so we found that fluid benchmarking increases this correlation quite a bit. And like here, I'm just showing one example, which is like the final 30% of training for, I think, all more evaluated on one checkpoint. On the left-hand side, you can see that evaluated on one benchmark. On the left-hand side, you can see that for standard evaluation, we don't really see any strong training signal. But if we look at the ability that we estimate based on fluid benchmarking, we still see that we are making progress. And the reason for this is because we know the difficulty of the items, and we take this into account. So even if the accuracy doesn't change, the model might learn to solve the more difficult items still, so the ability can still go up. And so if we take a quick look at the summary, we see that across all 3 or 4 evaluation dimensions, efficiency, validity, variance, and saturation, we always improve using fluid benchmarking compared to standard evaluation. And we also improve compared to other methods that have been proposed in the past. So we looked at a couple of other methods like tiny benchmarks, meta bench, and a few others, and we improved compared to them as well. So we are very excited about this, and we see a lot of potential for future work. And before I open this up for questions, I want to quickly highlight 3 lines of work that I'm particularly excited about. So for one, I think we need a much better theoretical understanding of the limitations and best practices of using IRT in the context of LLMs. So in a way, we just what we did and what other people did was we just used certain heuristics about how to pick the LLMs to train the IRT model, but there are many statistical and also conceptual assumptions that these models, like the IRT models, make, where it's not really clear whether they hold for LLMs. So I think there's a lot of really interesting work that could be done in that area. Then secondly, I think there's a lot of relatively straightforward extensions of fluid benchmarking that we can think about. So for example, going from this item by item protocol that we did to something like multi-stage training, where you have individual stages that are non-adaptive, but then after each stage you do an ability estimate, and then the next stage is going to be picked based on that ability estimate. We only used unidimensional IRT models, so the item parameters just had one dimension, but there are also multidimensional IRT models which might allow you to capture even more fine-grained patterns that exist in those benchmarks. There are things like dynamically stopping the evaluation, which we experimented with a little bit, but we didn't really explore it in too much detail. Looking at for example, agent evaluation in some sort of fluid setting. I think there's a lot of interesting things that could be done. And then finally, this idea of adapting items to the capability level of an LLM could also be really useful for training. So there has been some early work doing this before. I think this was still before like the big wave of LLM progress. So I think it would be super interesting to try this out in the context of more modern training regimes. And yeah, I think that having this dynamic nature could be very useful for training as well. All right, thank you so much, and I'm very happy to take questions.
Awesome. Yeah. Thank you so much. I think that was I learned a lot from that. So I think yeah, if people have questions, please put them in the chat. There's a couple that I think we didn't get to, but yeah, I had a couple of questions that maybe I can kick off the discussion with. One thing I found interesting is this notion of discriminative power. And I was wondering if you had any intuitive sense of kind of like how the discriminative power changes when new LLMs might enter the mix. So like, let's say we compute the discriminative power with respect to a set of LLMs. And I guess like, how does it generalize to different LLMs, basically?
That's a great question. For new LLMs, I would be more worried about the difficulty than the discrimination. I think, yeah, I need to think whether there could be a case where, I mean, of course, I think you can theoretically create a case where you add in a couple of new LLMs and the discrimination, of course, changes. But in practice, so like what this discrimination parameter essentially measures is the following. Imagine you create 2 rankings of the models. One ranking based on the full benchmark. So you rank all models on MMLU, for example, and then you rank all models just on this one item. So the second, if you have like a standard multiple choice setting where it's just like correct, incorrect, the second vector is going to have like all the models that got the item correct at the top, and then all the models that got the item incorrect at the bottom. And then you compute the correlation between these two. So there are certain ways of doing that by serial correlation, for example. And items that have a high discrimination will have a very, very high correlation there. So all the models that got this item correct are overall also the better models. Now, if you think about, if you add in, if you have a high discrimination item and you add in a new LLM, of course, if you have a very strong LLM and all of a sudden this LLM can't solve this item anymore, yeah, then it could change. But I'm not sure how often this would occur. Like one case where this could occur is if previously an item was very easy or had a low discrimination for contamination problems. So like contamination could also be reflected in discrimination because some of the models which are otherwise very bad might get this item correct because they have seen it in the training data. So if there's one item which shows up in a lot of the training data sets, it could have it could be one reason for low discrimination. And now imagine that all of a sudden people get more aware of this and they actually remove this item from the training sets. It could increase in discrimination over time. But like for difficulty, it's much more obvious why if you have like a new cohort of LLMs, all of a sudden a certain item that used to be very difficult in the past is at the moment not so difficult anymore. There's also the problem, like one problem that you have is, imagine you have an item that none of the LLMs in your training data got correct. This is gonna be like all those items are gonna get the maximum difficulty. So there's no way of distinguishing between those. And now imagine you have like better LLMs, and now all of a sudden some of these items that seemed impossible in the past all of a sudden can be solved. Then you would get these like more fine-grained distinctions that previously you couldn't really get. I'm taking this psychometric approach. So for difficulty, I think this is a bigger problem.
Yeah, I think that makes sense. Yeah, I think the point you mentioned about if it's in the training data, then the discriminative power, like that will reflect in the discriminative power. So I was basically thinking of like discriminative power as related to like the saturation plot, for example, you showed in the beginning. And like intuitively, it seems like if the discriminative power of an item reduces when you add a new LLM, it could be, one of the reasons could be that it was actually trained on it.
Yeah, I agree. Yeah.
Um, cool. Okay. And then another question I had was kind of like, I think you mentioned this at the end of the talk, but some benchmarks have LLM as a judge. And while the score assigned to an item, like you could still apply this in its exact form. But I'm wondering if there's anything new to consider there in terms of like item response theory. I guess as long as you keep the judge the same, nothing should.
Yeah. I think as long as you keep the judge the same, it should still work. Even like when you change the judge, so I think it gets very tricky when you try to compare, you use IRT and you try to compare evaluation results where you had different judges. But I think I think even if you have a new judge which is different from the training judge, like the judge that you use to fit the IRT model, that could still work. I think, yeah, that would be interesting to experiment with. I could see this could still work, even if you switch the judge. But
Yeah.
yeah, that could be something to try out.
Makes sense. Yeah, I feel like as long as the judges are roughly similar,
Yeah.
It should.
Yeah. Like in general, this is all super interesting research for the future. I mean, if you look at these papers, these IRT papers, I mean, including our paper that are being published, they all look, I mean, they typically look at the OpenLLM leaderboard because it's just very easy to fit IRT models there. You have a lot of models. But I mean, yeah, these benchmarks, for one, they are not the most challenging benchmarks that we have. I mean, they are like maybe even two generations behind what we have at the moment, and they also don't take into account many of these more recent kinds of evaluations, like based on LLM as a judge. So I think there's a lot of really interesting work that can be done in the future.
Yeah, I feel like what's beautiful though is that this can generalize to those kinds of harder evals
Yeah.
that you mentioned.
Yeah, like the assumptions that you make are very limited. I'm also thinking sometimes whether this term psychometric is, I don't know, whether people whether it misleads people that this has something to with psychology or something like that, because it makes only a very small number of assumptions about items, about models. So I think, yeah, it's applicable in a quite broad range of applications.
Mm-hmm. Cool. Yeah, I had one more question, and then I do see a few questions in the chat. I think like one of the things you mentioned was this could potentially be a way to identify, at least in the MMLU Redux case, mislabeled items. And I found that quite interesting because, yeah, if you have an item that no LLM gets, that's going to be pushed to the end of your fluid evaluation. And yeah, I'm wondering if this method could actually be used explicitly for that as a way of filtering out, like if a benchmark has 30% of items that are mislabeled, then maybe this could be a way to, as a first pass, detect that.
Yeah, totally. I think that I mean, I didn't include this here, but one analysis that we did, I mean, for this year, we took MMLU redux, right? So we also measured how high is the discrimination of those items that annotators actually said are mislabeled based on the OpenLLM leaderboard. And you see this separation of the low discrimination items or of the mislabeled items that have a low discrimination and the non-mislabeled items that have a much higher discrimination. So you could do, as somebody developing benchmarks, I mean, you could hire annotators. You could also say, I'm just going to evaluate a range of models. I'm going to compute the discrimination of all my items, and I'm just going to remove the lowest K% of items, where K you would need to determine somehow. And that would remove many of the mislabeled items without having to hire a human experts. So yeah, that could be done. Like one problem is when you are not in the position to design the benchmark. I mean, in the end, people are going to be interested in your MMLU numbers and not the MMLU filtered, right? So yeah, I think, but if you are in the position to actually decide this is going to be the benchmark, I would absolutely recommend doing that. Yeah.
Yeah, that makes sense. Yeah, and you can do things like, if like at least one model gets it, then it's way less likely that it's mislabeled, or maybe not. Yeah, there's a
I
lot of
mean, so the discrimination is different from the difficulty, right? So you really need to look at the rankings of all the models according to this one item and the ranking of the models on all the items, right? So it can be in a way like discrimination, like there's some connection between discrimination and difficulty, but you can have a high discrimination item that is very difficult or high discrimination item that is very easy, right? So a high discrimination item that is very difficult would be an item that is very, very good for distinguishing between super strong models and strong models, for example. It's not good at all for distinguishing between weak and very weak models. And the same can be true for an easy item.
That makes sense. Yeah, thank you for that. I think there's a couple of questions from Prashant. Prashant, I think you should be unmuted, so feel free to ask them live.
Sure. Hi, Valentin. Very nice talk and very intellectually stimulating work, I have to say. It's not often that you come across papers like that.
Thank you.
But I had a bunch of questions. I guess in the interest of time, we could maybe go in the reverse order of how I have listed them. The first question would be I guess, yeah, I mean, you did mention at the end of your future work slide about training methodologies based on this kind of difficulty estimations and all that. So have you more specifically thought about like curriculum learning and how that aligns with your work?
Yeah, you could do something like curriculum learning where you just order the items by the difficulty, for example. You can even do more sophisticated things, right? Because it could be, I mean, if you think about it, like for curriculum learning to be effective, the progression in difficulty needs to align with the progression in ability of your model. But it could be that your abilities develop much quicker than the difficulty in your item. So in a way, you would still train on items that are too easy and until you reach items that are more useful. So you can, I mean, you could, for example, have an underlying IRT model that you always use to estimate the ability. And then based on your current ability estimate, you would pick the next training item. Of course, for that to work, you would need to have some sort of model that would tell you if this is my ability, then the difficulty of an item to be effective for training should be such and such. So I think that there's still like some work to be done. Like what is a good connection between the ability of the model and the difficulty of an item to be an effective training item. But there could be some ways that are more sophisticated than just the vanilla curriculum learning approach.
Sure. Sounds good. My next question was I'm not sure I've thought through this completely, but Does this make sense to, or if you actually ran any studies for human evaluation, or like say using humans as judges to judge difficulty and discrimination for items and see how well that correlates to whatever IRT gives you, just on a let's say even like a small sample size?
Oh, I love this question, and I would love to do this study. I haven't done it. I am thinking about this a lot because um, I don't think that difficulty for an LLM is the same as, for example, difficulty for a human, right? We did one analysis where we looked at different MMLU subsets and we looked at the difficulty of the items. And you see that, for example, there's some overlap between elementary math and college math. So some of the college math items, according to the LLM trained IRT model, are easier than some of the elementary math problems, where
I
I would
see.
assume that for humans, you would have a very neat split, and
Right,
all the college math items would be much more difficult than any of the
right.
items in the elementary math. So yeah, it would be very interesting to analyze this. And then if you see big mismatches, wonder why is this? It could be that there's something like contamination happening. Models have just seen items that are very similar to that in the training data, and maybe some of the elementary math problems are just very different from in terms of how they are phrased, how they are formatted from anything which was in the training data. So yeah, I would love
Right.
to do this study. We haven't done it yet.
Or maybe I don't know if it would make sense if you had like different training epochs of all the different models that you used for training the IRT model, and see how like, well, no, that, yeah, I'm not sure. Yeah.
Yeah.
Never mind. I was thinking out loud. But yeah, okay. The last couple questions, I think these are like fairly low level ones. So, how do you pick models for estimating the IRT model, and how do you determine sample size for efficient evaluation using IRT?
Yeah, that's a good question. I mean, like we just tried out different numbers of items. You can do this more systematically by looking at the error on your ability estimate. So you, in a way, you can compute how precise your ability is based on all the items that you have evaluated. And you can, for example, put a threshold on that and say, so the like this error goes down and down and down as you do the fluid benchmarking. And you can define a threshold and say, whenever my precision or like my standard error is below the threshold, then I just stop the evaluation. And we actually did an analysis, and we have it in the paper, where we show that as you train the model, the number of items you need to reach the same precision actually varies. So it, in a way, saying like even having a static number of items is suboptimal. Ideally, you would also want to adapt the number of items to the current state of the LLM.
Okay. Makes sense. And yeah, the other question was like, how do you pick models for estimating the IRT
Yeah.
model?
So that's a great question. I mean, this is was also quite related to this first point. I mean, we did certain heuristics, like so IRT makes this IRD assumption that all the test takers are independent. So for example, we removed um, base and instruction tuned version. So we only had llama base and not also llama instruct, because I mean, they are very clearly not independent. We also didn't include merged models. So we had some heuristics to remove many of the models. And then we had some sort of cleaner set of models comprising, I think, 102 models that we in the end used to fit the IRT model. But as I said, I mean, we did not experiment a lot with what would happen if you were to include the instruction tuned models. Is it really a problem? Maybe instruction tuning changes the model in such a way that you can treat those as two different test takers. So there's a lot of very interesting work that can and has to be done, I think, in the future.
Yeah. And I guess this could relate to the other point that you were saying, that you would want to analyze how humans judge this,
Yeah.
so as to better pick models that kind of align with like how
Yeah.
humans would think, maybe.
Yeah.
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 Sure. Yeah, thank you so much, and great talk. Thanks.
Cool. Awesome. There's a couple of questions from Jacob. The first one being, can you share more about what kinds of multi-dimensional IRT models might be applicable?
Yeah, that's a great question. So, like in a multidimensional IRT model, the the items are multidimensional and the test takers, so the models, are also multidimensional. And so what this can be, what this can allow you is you can, for example, model different dimensions of capability. So you could, for example, imagine that one dimension captures reasoning capabilities and then another dimension captures coding or something like that. And the idea would be that you would not need to specify this in advance, but it's very similar to training word embeddings or something like that, where like you would train them, and then in the end you would need to figure out where's actually this semantic dimension captured, right? It might not be in like one orthogonal dimension or something like that. And so what you could do is you could come up with a multi-dimensional IoT model. So typically these have like 5 dimensions or 10, so they are not as they don't have as high dimensions as, for example, we would use for LLM training or word embedding training or something like that. But you could create a set of benchmarks of varied nature and then fit a multi-dimensional IoT model on this collection of benchmarks. And then you would hope that certain similarities across benchmarks that you can't really capture when you fit individual IoT models to all of those benchmarks, that they would show up. So there could be, certain, MMLU items that are very mathy because they are math subsets, which are then more similar in terms of their IoT parameters to Hendrix math or something like that than other MMLU items. So you could capture these latent similarities between benchmarks better.
That makes sense. And we'll do one last question and then maybe call it. But yeah, Jacob says one study I'd personally be interested in is whether non-discriminative items as judged by IRT correspond with items flagged by human annotators. I think this ties back to Prashant's point earlier as well.
I mean, so we did this analysis for MMLU, and there it seemed to be the case. I mean, there's still some overlap. So like when you do the analysis, you see there's like 2 groups, and if you do a t-test, the average discrimination is much lower for the flagged items. We did not really try it as a classifier. So there's some overlap. So there are some items that are low discrimination and they are not mislabeled. Because I mean, there can be other cases, like we mentioned contamination. An item can be taken for itself super valid and not mislabeled and so on. But if it appears in a lot of the training data sets, it can still be low discrimination. And there are other factors. An item might just not be a good item for LLMs for whatever reason, right? But it would, of course, be very interesting to extend this analysis and look at other benchmarks as well. Yeah.
Cool. Awesome. I guess more of a brainstorming question that I have. Like, it seems like there might be some way to adapt this to a new benchmark. So rather than having pre-computed item scores, and this is completely like I'm just brainstorming, but maybe you have a new benchmark and then you run a set of K models on the first item, and you have some adaptive estimate of like difficulty, and then you can like active learning style kind of like pick the next best question. I'm curious if you have thoughts on that or if you've thought of that before. So rather than
that's an interesting idea. I haven't thought about this. So how would you pick the second item then if you don't know anything about the items? Or would you use the item, the question text or something like that?
Well, I think there's 2 ways you could do this. One is like you maybe run a suite of a couple of LLMs on the first item and then use their responses to get a sense of discriminative ability of that item. And you maybe have some assumptions on like how the items are related.
Yeah, that would be very interesting. That would be very interesting. Yeah.
Anyway.
Like in general, there is this alternative approach to modeling items via looking at the item text or like other properties of the items, which is like more intrinsic. Like in a way, this IoT approach is very extrinsic. You say like, oh, I look at the model behavior on those items, but the items are black boxes taken from themselves. You can, there's also ways of really looking at the items. What is actually the question about, like, and so on. What is the item text? And thinking about how to combine these 2 approaches, for example, in a scenario such as the one that you described, would be very interesting. Yeah.
Cool. Makes sense. Awesome. Yeah, thank you so much for this talk. I'm going to paste the paper for reference in the chat if people want to look at it. But yeah, with that, thank you all for coming. The recording will be up shortly. And thank you so much, Valentin.
Yeah, thanks for having me. I really enjoyed it.
Awesome. Thank you. See you, everyone.
Bye-bye.